So let me start off by introducing myself. I'm Lara Petrishchev. I'm with Emerson, specifically part of the Measurement Solutions team, and I'm a refining and sustainability marketing manager, but I am a chemie. So today I'll be talking to you guys about lowering greenhouse gas emissions by crude selection. So first off, there are two trends running in the global refining market. The first being is that oil-producing countries are still trying to leverage their crude resources in hopes that those crudes will be converted to profitable refined products. The second is a reinvention of the sector to align with the long-term demand of low-emission fuels. So what I have here is a generic graph that was published by the Hydrocarbon Publishing Company. Now take this graph with a grain of salt because the greenhouse gas emissions can be quantified in different ways, and it's certainly dependent on the configuration of a refinery, the technologies used, as well as the efficiencies of those technologies. And so crude is often categorized by the API gravity, which is essentially a density measurement, and the sulfur content. You'll hear sweet crude, meaning it has a low amount of sulfur, and sour, meaning it has a large amount of sulfur. And here, as you can see, if someone was looking at crude selection to reduce greenhouse gas emissions, that doesn't always correlate to low sulfur, which can convert to SO2 emissions when combusted. Now you can, desulfurize via hydrotreating, but that will require more hydrogen usage. And so that'll also result in more energy intensity as well because you're using energy to create the hydrogen. Another factor to consider is that the sulfur is going to result in some corrosion mechanisms such as sulfidic or sour corrosion. So these are things to look out for when you're selecting your crude feedstock. And now here I've highlighted some key methodologies on how greenhouse gas emissions are quantified. The first being the well-to-wheel analysis, and that's essentially tracking the crude from extraction to refining and then eventually wheel road transportation use. Next is life cycle assessment, which is a more holistic approach. It actually considers the materials being gathered and the greenhouse gas emissions generated from the materials needed, not just looking at the crude. And then there's emission factors. A lot of times you'll get these emission factors from EPA. Always look at what the emission rating is for those emission factors. If it's got a D rating, that's not a good sign. Maybe you might want to generate your own site-specific emission factors to get a better idea of what you're truly emitting. Next is the carbon intensity measures. When that quantifies the amount of CO2 generated per unit of crude, and oftentimes that is associated with a life cycle analysis. And number 5 here, measurement, reporting, and verification systems. A lot of that is covered in 40 CFR 98 subparts Y and C. So those are your different tier calculations, which include SIMs and using emission factors in the equations they've laid out there. Number 6 is simulation models. So that's something I'm going to be talking to you guys about. Emerson is working with Aspen Tech to figure out how we can work together because we provide the instrumentation, which will give you quality data that can be put into these simulation models. So don't just look at software in itself. That's how you get the garbage in, garbage out scenario. So here I have a well-to-wheel analysis for crude oil. And as you can see, the majority is from the end user being combusted. So really what refineries have a control over is like 10 to 15%, and that's including the upgrading. And what makes renewable feedstock so appealing is the fact that they don't have the oil extraction and production piece, that's 7 to 10%. So crude blending is something you should really look into because say you have 2 different types of crude, maybe 20 to 80% of these 2 different types might be fine, but then if you shift from that to 30 to 70, you might actually cause some fouling and shutdowns in your heat exchangers as well. So that blend ratio is something that should heavily be controlled and monitored. Another thing to look out for is the paraffinic content in crude, because that'll cause wax deposits to build up in the pipelines. And then you will need to either do some dilution, insulation, and that will result in a higher energy intensity as well, because you use higher temperatures to ensure the fluidity through the pipelines. So it's, you might have heavy crude, which is moderate in sulfur, but not in paraffinic. So these are all things that you should consider. So this is a fully instrumented heat exchanger that I have here using all Emerson's instrumentation. We have a lot of wireless products that we've showcased before. I'm sure if you've sat in on any of the other presentations, you've heard of our X-Well technology, and what that does is takes the ambient temperature and the temperature of the surface of the pipe, and it uses a thermal conductivity logarithm to figure out what the process temperature is inside. But what's new to our profile is this FlexSim flow meter, which is a clamp-on ultrasonic flow meter, and it can detect buildup in your pipes, and it's perfect for viscous and high temp applications as well. It could also simultaneously measure 2 lines at once. Eventually, this will be built into our diagnostic tools, but right now they have their own. What I have here is a screenshot of our PlantWeb Insight app for heat exchanger monitoring. So all of this data can eventually be used and correlated to your crude slate. And so here is an example of a crude blending solution. So what you see here is multiple crude tanks using a Coriolis meter, and they have a blend controller. So then you can make sure that you're staying at that 20 to 80 and not reaching that 30 to 70. In the past, they used to use turbine meters, and those are not very accurate. As you can see, it's about 0.5 to 1.5 versus a Coriolis mass flow meter, which is 0.1 to 0.05% accuracy. And with that Coriolis meter, you're getting not only a direct mass measurement, but also direct temperature and density. So there's a temperature sensor that's built in, and the mass is calculated via inertia, and then the density is calculated by the resonance frequency between the oscillating tubes. So with all of that, you have your mass and density. You could then have referred volume and net concentration measurements. And then with the blend controller here, as I said, you can have a set point. So what I have here is a video that Aspen Tech showcases that shows their mass balance software, which you'll hear them talk about Aura in detail, and how a bunch of their products can be used to quantify greenhouse gas emissions and figure out which units you should focus on. So I'll go ahead and play that video. Uh-oh. Let me figure out the audio. Hold on one moment. I'll just grab someone from IT.
Why not read them?
Excuse me? I could go through my other slides until we get someone. So what we have here is a Coriolis flow meter that is used for fuel on a fuel line for a fired heater. And what makes this superior to other flow meters is that, again, it's a mass flow meter. And as you can see here with a refining fuel glass, there's a lot of variation in the composition. And in the energy content is more related to the mass versus the volumetric. And so that's why you would want to use a mass flow meter, because then you're more likely to get to your target air to fuel ratio. And then with less excess air, you're also reducing NOx and increasing your energy efficiency. So what we have offered here is a new G series Coriolis, which is a very compact and most affordable Coriolis meters, because most of the time when we offer the solution, they're like, it's great, but it's too expensive for us. So now we have something that's a little bit more affordable and it's certainly going to pay back and you know, not only reducing greenhouse gas emissions, but NOx as well. And so I talked to you guys earlier about corrosion mechanisms. This isn't only prevalent with crude selection. If people are looking to co-process in their FCC unit, you should certainly look out for corrosion mechanisms. In fact, we have developed an entire white paper on the various corrosion mechanisms occurring in either the offsites, reactor operations, and the pretreatment section as well. So what we offer at Emerson is ultrasonic thickness sensors. And so it's measuring the thickness of your pipe wall. And it's also connected to PlantWeb Insight software. Real-time monitoring, but now this data can be used for predictive monitoring. Again, we're working with Aspen Tech because in the past, refiners had to develop their own software and how to utilize this data. And so here's an example of the certain the data points that you would get from manual ultrasound measurements. A lot of times you'll get inconsistencies because of human error. And now let's look at the possible trend lines you could get with this data. And now let's compare it to PermaSense, which is retrieving 2 data points per day. So you have a solid trend line and you've kicked out the outlier data points. And so injection to inhibit corrosion. This is an example from a European refiner who used our sensors to figure out exactly when to inject because it is very expensive to do these injections. In fact, they use Coriolis meters just for the chemical injection as well. So overall, these are some of the best practices. You know, energy efficiency is a big one. In fact, I've with my team developed an entire ebook for best practices for energy efficiency with steam distribution, combustion control, and distillation column optimization. All that stuff, if you would like, feel free to approach me and I'll give you more information on that. Carbon capture, we are developing more content on point source carbon capture. We've worked with some large companies to achieve this. It's been done in Canada, but we're trying to increase the carbon capture efficiency in the future. Then there's waste heat recovery. That's certainly very important and an easy way to reduce emissions and just, you know, any utilities that you use. And as well as plant management, just making sure that you have the regular monitoring and auditing of the plant performance, process optimization, which involves controls and instrumentation, and then fugitive emissions management, which there's several discussions about here at 4C, and then also good employee training. So making sure that everybody has the same values, the corporate sets. So not just for environmentally friendliness, but also with safety. Because when we talk about corrosion, you have to monitor that also for a safety aspect. So you're not putting someone in an environment where there's toxic fumes or flammable fumes being released into the atmosphere. So that is all I had. However, I'm going to go back to my video, and hopefully someone is coming from IT to help us out. So one moment, I will be right back and trying to find someone. Usually they're right outside the door. So please excuse me, I'll be right back. That's okay. Negative. I'm not hearing it. Should I keep trying?
This brief demo will introduce you to AspenTech's
Oh, there you go.
new emissions management solution.
Me.
Let's start by looking at the enterprise view for a refining company, focusing specifically on carbon scope 1 and scope 2 emissions, refining margins, and carbon taxes. It's important to note that this dynamic enterprise interface is fully responsive, able to be viewed on a large operations center video wall or a handheld mobile device. The enterprise view is fed in real time by underlying modeling applications, such as Aspen Lara, that calculates emissions based on available plant data and reporting rules. The model from Aspen Unified Planning identifies planned margins, yield, and carbon emissions. Now let's look at the company's refinery in France, where we can see the emissions are 50% higher than planned. This immediately tells the management team that mitigation measures must be taken to get carbon reductions back on track for the year. From here, you can drill down and look at other metrics for the site. This graph breaks down the major emitting process units. The blue bars indicate the planned CO2 levels, while the yellow bars show the actual emissions. You can see here the fluidized catalytic cracker, or FCC, is the largest emitter and the most overplan, followed by the site's utilities and on-site hydrogen plant. Managers may prefer using the bar charts, but the solution also provides a flow sheet view, giving flashing red visual cues as to which units the technical team should focus on. Using the solution's integrated digital twin models, engineers and operators can easily identify major carbon emitters and recommend back to managers where to take action. By visualizing the conditionally colored indicators in the flow sheet and then drilling down into the connected apps, we can quickly isolate major offenders and determine the root cause. In this case, emissions from the FCC, the utility system, the hydrogen network, and crude distillation units exceed the planned emission levels. A key benefit is that everyone responsible for a mitigation plan is working off the same data and same system. Plus, everyone has full visibility into what others are considering. Before taking action, the team will want to prioritize steps based on CO2 emission and profitability associated with individual process units, and can share these steps with the sustainability and operating teams for rapid and informed decision-making. The FCC drill down helps you see the specific opportunities for improvement. Here, the process engineer accesses the same system to identify the root cause using AI-assisted models and determine operating changes, including temperature and throughput rates that can reduce CO2 emissions, while also maximizing revenue opportunity. Here, the FCC engineer works from an Aspen hybrid model of the unit that is frequently recalibrated with plant operating data. The model combines first principles and AI modeling, rapidly updating the model to current conditions and running hundreds of predictive models in seconds. Non-engineers can see a simple curve that shows the impact of operating choices on CO2 emissions and the corresponding specific product yield in the FCC. The dispersion plots show different operating regimes and the associated CO2 emission levels. In today's high-margin gasoline environment, the AI-based model's features are key in determining the optimal riser top temperature that minimizes CO2 emissions while maintaining maximum FCC throughput and light crack gasoline yield. This can be adjusted to give operators the key options in any economic situation. Summarized information from the planning model tells you with a simple bar chart that with the new operating condition, you are able to reduce CO2 emission and achieve increased profitability. This now becomes one option for CO2 reduction, and the other teams see the results of the FCC technical group's analysis. Now we turn to the crude units, where a similar drill down shows that actual emission levels in the CDU are also higher than the plan. In this case, there is also a higher energy consumption than the benchmark. The cause could be poor hydraulic performance at the distillation units or fouling in the preheat heat exchanger train. We can quickly look at both with this solution. A unique and powerful visual display shows the internal performance of the column. It's easily readable by others in operations. In this case, we quickly see that hydraulic profiles are within the recommended operating envelope, so that is not the cause of the emissions delta. Turning to a more detailed flow sheet, we see a heat exchanger is flashing, leading the technical team to check the fouling rate in this unit. Sure enough, one of the heat exchangers is at a threshold, meaning reduced efficiency, excess fuel consumption, and higher CO2 emissions.
Okay, I won't play the entire video, but you get the gist of it. And another thing I'd like to mention, when I showed you the fully instrumented heat exchanger, all that instrumentation is not required for a preheat train. You can use fewer instrumentation to monitor your preheat train. So since I've already gone through all of my slides, I would like to, ask the audience if you guys have any questions for me. Is anybody using Aspen Tech right now for any simulation models? No. Well, now since Emerson and Aspen Tech are working closely together, hopefully that will change and we can use both quality data via instrumentation and software together to provide a packaged solution. So if you'd like to contact me, I've provided my phone number and my email as well as our North America refining business manager, Warren Merriman. So feel free to take down our contact info. If you think of any questions in the future, don't hesitate to reach out to me. Thank you all for your time, and also feel free to stop by our booth, E3 and F3 and